Hello, my lovely 12th standard warriors. Welcome to the Pathfinder series, the Semiconductors chapter. All that we have today is we're going to talk about the semiconductors, the PN junction diode, and also the applications of the PN junction diode. And all of this is with me, your physics master teacher at Vedantu, going live. Hello, everyone. How are you? And are you guys excited about the session? Do let me know in the chat box. Let the chat box be lit because it's an important class. It's important for JEE Mains. It's important for even the NEET examination. It's also important for the boards. And in the recent years, there have been questions coming from this chapter. They are super duper easy, theory kind of chapter, and very direct questions can come from this chapter as well. And sometimes it could get little tricky, so we are going to do those kind of questions as well. So here is the flow of the class, and this is lecture 1 of semiconductors and diodes. And we are going to see the energy band formation, what is this energy gap, and what is this PN junction diode, and what are the different kinds of semiconductors, how you can dope it and classify it. And then we are going to see the biasing of PN junction, the characteristics, and then we are going to move towards the diodes and the different kinds of applications like LEDs and Zener diode, of course, and lots of amazing questions coming up over there as well. So all of this is with me, your favorite physics master teacher at Vedantu. And how are you guys? Do let me know. Are you guys excited about this session? This is the Pathfinder long-term free series on YouTube on Enthuse, the dedicated English medium channel. And I have been training kids for a very long time, and trust me on this, it takes a lot of effort from both students as well as the teacher's side. So I started this Pathfinder series so that everybody gets quality content with problem solving, with the theory and the application of the concepts for getting those problems right. And I'm so glad that this series is coming almost near to the end, and I'm so happy that you guys have stuck around. And those of you who have stuck around, do let me know in the chat box when you joined Enthuse, when did you learn about the Pathfinder series, and if you have any backlogs, do let me know about that as well. Maybe some of you were able to watch only maybe, I don't know, 10, 15 videos or 20 videos. So it's okay. Do let me know so that, I get a sense of what kind of audience I have. And yes, please go ahead and smash the like button out there. And thank you for filling the chat box with all your love and all your hearts and all your support. It means a lot for me, the channel, and the team which works behind this. Go hit the subscribe button because lots of amazing sessions coming up in the days to come, so that we guys make sure you excel in JEE Mains, JEE Advanced, and boards. This channel, if you have been following long enough, we prepare you for boards. Before the boards, I conducted marathon. Before BitSat, there will be mock tests. Before mains, you know what we do. And advanced, of course, we do advanced session as well. So all of this is going to come through on this channel. And you want additional support. You want to make sure that you improve from wherever you stand right now. Trust me, Vedantu can help you. A lot of our students who joined Vedantu have improved their percentiles and their ranks. Even if their ranks were very low, before, our methodologies and our systems have helped them achieve very good, amazing ranks. And that's the reason why thousands of the students have got amazing percentiles, not just in advanced, but also in mains. So if you want to check out one of our courses, do check out the link which are there in the description box, and you can see, you can learn right from home. You get everything, tests, assignments, recorded classes, live classes, everything. So at the comfort of your home. And remember, you have to use my coupon code so that you get that additional maximum benefit at affordable prices. So that's what we stand over here for, to make sure that every kid gets quality education at the right price. So let's get started with the session. And here is the first question coming up in front of your screen. I want the chat box to be flooded with the answers. I'll read it out for you. The resistivity of a semiconductor is dash on the voltage and dash of the temperature. But For conductors, the resistivity dash on the voltage and dash on the temperature as well. Meaning you have to fill in the blanks with words like dependent or independent. Does the resistance somehow depend on the voltage or the temperature for semiconductors? And what about, conductors? Does it depend? Does it not depend? Think about it and put it up in the chat box. Keep the josh high. I'll be seeing the chat box. Trust me on this. Okay. I hope you have made up your mind. And in case you're still watching it recorded, you can always pause the video. And if you're joining this class live, you can catch up the missed part at any given point of time. Even pause the live class. You can go back, replay the same parts again and again. So that's the best part of learning on YouTube as well. So the correct answer is dependent, dependent, independent, and dependent. Now let's understand why this is so and what it means actually. See, conductors meaning copper, aluminium, all these are conductors. Insulators will be like ceramic, plastic, rubber, wood, paper. They are all non-conductors or insulators. They do not conduct electricity. Semiconductors lie somewhere between conductors and insulators, and semiconductors show very unique properties. We all have seen that, oops, 1 second. Okay, let me just get back the screen. It just became small. Just 1 second, my warriors. Just 1 sec. There we go. Okay. Yeah, let me just get back our screen. Yeah, so what happens is we have seen that resistance depends on temperature, and there are laws for that. R naught alpha delta T is the change in resistance. You would have seen that in current electricity chapter. Hence, resistance depends on temperature. Now, whether it is a conductor or a semiconductor, it will depend. Whether the coefficients are positive, negative, big, small, we'll talk about it. But it depends. If you change the temperature, resistance changes, both for conductors as well as semiconductors. But this is one interesting thing. The resistance of a semiconductor depends on the voltage. Like, yes, sir, that is true, right? Because you will be thinking R and V are related by this equation, V is equal to IR. You will be like, obviously, if voltage increases, resistance increases. Wrong. If voltage increases, then the current increases for the same given device. For a given device, the resistance is constant. So if voltage increases, the current increases. Resistance remains constant for a resistor. But for a semiconductor, the resistance depends on the temperature also. In fact, it has variable resistance. It shows variable resistance property for different voltages. So that is one distinguishing factor for a semiconductor. Also, let me tell you, for conductors, the temperature dependence is something like this. You increase the temperature, the resistance increases. But for semiconductor, it's quite different. If you increase the temperature, the resistance goes down. So that's the second difference that is there between a conductor and a semiconductor. So what are the two differences, my warriors? Come on, repeat before me and think in your mind. Number one, when temperature changes for a conductor, so temperature increases, resistance increases because collisions increase. But for a semiconductor, when temperature increases, resistance goes down. Why it happens, you will understand it. Don't worry. You have to stay tuned for the lecture, in the lecture now. And for resistance, dependence on voltage, understand, for a conductor, it remains the same. It's independent. But for a semiconductor, resistance is variable and depends on the voltage itself. That's crazy. So let's talk about all of this in today's class. I'm pretty sure now you're all excited to know what a semiconductor is, how it works, what are the basic fundamentals, and all the chips, all the computers, all the mobiles, all the cars, automobiles, so many things around us. Everything has a semiconductor in one way or the other. Don't you agree? And believe me, semiconductor is a very new technology, hardly 50-60 years back. Okay, so semiconductor has revolutionized the way things have advanced in today's world. And things are becoming smaller and smaller only because of these semiconductor devices. All right. So to start with the understanding of semiconductor, we need to go to very, very basic and slowly we'll build it up. Let's start with an example of a sodium atom. Okay. Sodium is a metal. All right. It has a valence electron out there. So you can see this is how the electrons configuration looks like for sodium of atomic number 11. Now, if you want, you can also write down the electronic configuration just for your understanding sake, right? It has in the 1s orbital, it has 2 electrons, and then in the 2s orbital also it has 2 electrons, and in the 2p orbital it has 6 electrons, but in the 3s orbital it has only 1 electron. Now, if you look at the energy level diagrams, as you know that as you go above to higher orbitals, higher orbits, the energy increases. Lower shells have lower energy. So 1s has the lowest energy and 3s has the highest energy. Now, for one single sodium atom, it will have the electrons paired up at different energy levels in their respective orbitals. Everybody agrees? Everybody makes sense out of this? Give a thumbs up in the chat box. Fair enough. Now the problem is, in this entire electron configuration and the energy diagram, there is one vacancy over here. There is one vacancy over here. Basically, it is not filled. And you know that atoms do not like empty shells. They do not like half-filled shells. They are not so stable. Either they want to get rid of it or they want to acquire an electron. Makes sense, right? Fair enough. So there is a vacancy. Now imagine there are, more sodium atoms. Okay, each sodium atom will have a similar energy level diagram. Each sodium atom, be it here, be it there, be it here, every sodium atom will have the same kind of electronic configuration, same kind of energy level diagram. Okay, fair enough. I know you're wondering, sir, okay, come to the point. Yes, I'm coming to the point. So let's talk about what happens when these sodium atoms come close to each other. Individually, this is how the electrons pair up in the energy level diagram. 1s2, 2s2, 2p6 and 3s1. 3p obviously is empty. When they come close to each other, then these energy levels start to interact with each other. Meaning, imagine if they are independent, okay, they have distinct energy levels, but when they come close to each other, these energy levels will interact and they form new energy levels based on their surrounding atoms. 1s of one sodium will interact with 1s of other sodium. Maybe there are 5-6 neighbors. They will all their 1s's will interact with each other and form a new combined energy levels. 2s will interact with all the 2s's in their neighbors. They will form new energy levels. 2p will also interact with their other 2p's. 3s will also interact with other 3s's and 3p's, etc. So the respective shells interact with the respective shells of the other atoms and they form new energy levels. And if they interact with 2 atoms, you will see there will be 2 energy levels of interaction. If there are 3 atoms or 5 atoms or n atoms, each atom will contribute to one energy line. So you will see n number of lines if n number of sodium atoms interact with each other. And it so happens like this. If 2 sodium atoms interact, let's say we are talking about the 1s orbital, 1s orbital of one sodium atom, 1s orbital of other sodium atom, when they interact, one of them will go up, one of them will go down. If let's say 2s interacts with other 2s of 2 sodium atoms, one of them will go up, one of them will go down. So if there are multiple sodium atoms, you will see one will go up, one will go down, and you will have n number of lines, few of them up, few of them down. You will have a bunch of lines interacting with each other. That's produced due to interaction of each other. You can see this. Very interesting. You can see 3 sodium atoms. Look at this. 3 lines of 1s. 2s has 3 lines, 2p also 3 lines, 3s also 3 lines. So they are all interacting with each other. That's why you are getting distinct lines. So this is the combined energy due to the interaction. Everybody clear till here? This combined energy, these are also called as the Fermi levels. Okay, fair enough. Everybody understood till this point? What if there are many sodium atoms? In a sodium solid, if there are many atoms, they are interacting with each other, you will have so many lines of 2s, 1s, 2p, 3p, 3s, everything, that it will be hardly distinguishable. It will hardly be distinguishable. That means you cannot separate out those two lines by a naked eye because they are very close to each other. There are many lines together, but they are there. Many lines are there. So instead of showing many lines, you call it as a band. You call it as a band. So when I say energy band of 1s, meaning all the 1s orbitals of all the atoms have interacted and formed many distinct lines. Together, collectively, those energies are called as energy band. Everybody clear what a band means? Everybody understanding this point? So a band is nothing but, so n lines, okay, n lines, n number of lines together, I can just call it as a band. This is just shown like this, you can just shade it. This is a band of energy. Now it plays a very important role while we discuss, semiconductors. One thing I want you to understand, especially for sodium, is that 1s band will be completely full because 1s is completely full of all the electrons. 2s is also full, 2p is also full, 3s is half full. That means the energy band of 3p, or 3p is completely empty, but 3s will be half filled. 3s will be half filled because every 3s orbital will have only one electron and one vacancy. That means it will be half filled. Everybody gets this point? So this is very important for all of us because we are going to define now two kinds of energy bands. Now that you know what is energy band, let's define two different kinds of energy bands. The ones which are completely filled, the ones which are partially or just unfilled. All the ones which are completely filled, they are called as the valence bands. What are they called? Completely filled, they are called as the valence bands. Very, very important. So completely filled bands are called as the valence bands, but the uppermost is called as the valence band. So filled bands are also called as the valence bands. So when it is in plural form, bands, S is there, then it refers to all the completely filled ones. But when I refer to it in singular form, valence band, I am referring to the highest. I am referring to the highest energy band of the valence bands. Is that clear? Give me a thumbs up. Give me a yo in the chat box. Fair enough, guys? Okay. The ones which are unfilled, they are called as conduction. They are called as conduction bands, plural. But the lowermost band, which is not filled, that is called as the conduction band, singular. So this is the lowermost. Usually in our day-to-day reference, we will be talking about singular forms, band of conduction or band of valence. Sometimes they also write this as, conduction band, CB. They also write this as VB, valence band, in short form. That's something which you should know. Got it? Fair enough. Now why the names? Valence, because it is completely filled. Conduction, because if it is half filled, or if there is an electron in these bands, those electrons are available for conduction of electricity. Imagine a half filled band, or by mistake some electron enters into those bands, the electron will become unstable and it is available for electricity's conduction. Hence the name conduction bands. Now Once you understand that yes, there are two kinds of energy bands, valence band and conduction band, let's also talk about the difference between them, the gap between them energy wise. You might have noticed that each band has some gap. So that gap also plays an important role in semiconductors. So that is called as the energy band gap. Please understand that no electron can ever stay in any of these empty spaces, because remember, when you talk about an atom, okay, even if you go back over here, an atom consists of electrons. The electron can be either in this state, this state, this state, this state. It can be in any of these orbitals. It can never have an energy outside these orbitals. Same way, when we have a solid, okay, and when we have bands, no electron can stay outside these energies. It has to be either in this or that. Okay, makes sense? Now, specifically talking about energy band gap, it is the energy difference between the lowermost conduction and uppermost valence. That means the conduction band in singular and valence band obviously again in singular. That is called as the energy band gap. Why is this important? Think about it. Why am I talking about energy band gap? The reason why I'm talking about energy band gap is because you can guess now, some electrons might want to jump for conduction of electricity from the valence band to the conduction band. That's when the conduction of electricity occurs. So for the conduction of electricity to occur, you might have to jump from here to here. That's why this energy is important. If this energy is too large, probably my electron might not be able to make the jump. And that's when electricity conduction may not happen. That's how we are going to distinguish between three kinds of materials as well. Everybody clear about this till here? Very good. So one more thing that I want you to understand before going to the next slide. You might have seen this, probably a thermometer. Why is this thermometer there? And what are these electrons doing? Well, you might have probably not seen this very clearly, or you might have just ignored this letters over here. T is 0 Kelvin. This is very, very important. 0 Kelvin, crucial, very, very crucial. These energy diagrams are always drawn, usually unless specified otherwise, at 0 Kelvin, that is the lowest energy state. When you give it thermal energy, that means when temperature is more than 0, what happens? Atoms have energy, translation, rotation, oscillation, etc. They will collide. And when they collide, what is the first thing that will get bruised? Like if you're traveling in a car and you're driving with lot of speed, what are the chances of something getting damaged? What will get damaged first? Obviously the bumper. Next comes your engine and inside parts, and then comes your seats and all of that, right? Same way, an electron, the most exterior parts are the electrons on the outermost shells. So they will get bruised and they will get shaken off, and once there is a lot of thermal energy, these electrons will be thrown out. And if the thermal energy is enough, if the temperature is enough, then these electrons can enter into the conduction band. Got it? So at low temperatures the electrons come back, at very high temperatures the electrons go up in the conduction band. Interesting, right? So temperature decides how many electrons are there in the conduction band. Interesting. Now that you understand that at normal temperatures you will have quite a few electrons for conduction due to the thermal energy which can now conduct electricity, let's probably discuss the three types of energy gaps that you can get. Number one, the band gap is so large, that even at room temperature you are unable to push the electrons from here to here. See, what do you need? All you need is, due to thermal energy, these electrons should jump from here to here, right? That jump should be possible due to thermal energy. Now if the thermal energy is insufficient to push these electrons, then no electron is there in the conduction band. That's it. Conduction band means it's empty now. So what will you do? No electricity conduction will happen, because The electrons are unable to enter the conduction band. That's why they are called as insulators. Got it? So the band gap is very large. When the band gap is very small amount of electron volt, then the energy will be just sufficient. The energy will be just sufficient to push the electrons into the conduction band. At room temperature, you will see the electrons will jump over here, and these electrons are now available for conduction. That's why these are called as semiconductors. Okay, because not all the electrons will jump, few of them will jump, and those few electrons will jump due to the excitation by thermal energy will be available for conduction. And then you will be like, sir, what happens in a conductor? Look at this, guys. The bands overlap. Yes, a lot of you might have had that question. Sir, can the bands overlap? You would have put it up in the chat box. You know? Yes, they can overlap. And if it overlaps, that's the best thing. There is no barrier, there is no gap, there is nothing that you have to jump. So if you don't have to jump, you can just walk in. It's like two rooms, the door is open. So you can easily go from here to here, and that's why you don't even need to heat it. So the electrons are available for conduction as it is. So this is the best kind of conductor. Hence, this is classified as a conductor. This is semiconductor because you need to heat it. This is, in spite of heating it, you cannot get the electrons to jump into the conduction band. Now do you understand the true difference between insulators, semiconductors and conductors? This is the true difference, okay, energy wise. Now, if this much is clear, my warriors, okay, if this much is clear, let's talk more about the semiconductors. This value of the energy gap is something which you should keep in your mind. Approximately 1 electron volt. That is the amount of energy which is required between the two bands for, you know, the electrons to just make that jump at room temperature. More than 1 electron volt, like 5-7 electron volts, it becomes an, you know, insulator. And when it overlaps, we just saw that it will become a conductor. Something which you should know. So keep these things in mind. I have put this up on the PDF as well. So very, very important pointers out here. And guys, I'm not sure if you have joined the Telegram channel. Have you? If you are not joined, please join the Telegram channel now. Some of you might have joined the old one. Make sure you shift to the new one. Why? You get updates, you get polls, we create some interactions so that we know what you want. Also, the PDF with the solutions of the homework are also available. So make sure you check it out. Okay, join it. You'll get everything, including my handwritten notes. Okay, now semiconductors can be classified further into 3 parts. I just told you insulators, semiconductors, and conductors. Now, semiconductors also can be classified. Now, how do you classify it? 1. Intrinsic. Next, extrinsic. I'll tell you what all these things mean. Don't worry. But what is the meaning of intrinsic and extrinsic? The name should ring a bell. Intrinsic means it is something which is inherited just because of its mere existence. Like mass is an intrinsic property of a particle. That means it is there the moment the particle comes into existence. Correct? So the moment you are born, you exist in this world, you have a face or you have some feelings. So these are all your intrinsic properties. Extrinsic is something which is affected due to external factors. Okay? So you can probably do something to it to change its behavior. So you can change its behavior 2 ways again. One is by p-type and second is n-type doping. And that's why you get 2 types of extrinsic semiconductors, p-type and n-type of semiconductors. You change the behavior, like, you motivate somebody to do something. You can motivate the person to do many things. So in this kind of semiconductor, you can alter its behavior by doing some alterations. P and N type, we are going to come to that. I know you might be thinking, sir, P stands for positive, N stands for negative. Well, you're close, but not that close. Well, let's talk about it. Before that, quick recap of the properties of semiconductor. Semiconductor will be like an insulator because at 0 Kelvin, what happens? All the electrons will go back to the valence band, correct? Only at good temperatures you will see the electrons jump to higher energies, and that's how they start conduction. Also, semiconductors can be modified by doping. Okay, modified by doping. I just gave you that thing over here. External factors, you change, alter the behavior which can affect the conductivity of the semiconductors. Very interesting thing that you can do with it. Also, the resistivity is higher than that of conductors but lesser than insulators. Yes, makes sense. The resistance is higher than conductors. It's somewhere between conductors and insulators. Makes sense. And the resistance of these materials decrease with the increase of the temperature and vice versa. This is something which I was telling you right at the beginning of the class. How many of you remember it? And now probably it will make sense. Why does the resistance decrease when the temperature increases? This simulation will help you. Go back over here. This simulation right over here. Look at this. When temperature increases, more electrons jump into the conduction band. More conduction means less resistance. That's why when temperature increases, the conduction increases. That's why resistance decreases for a semiconductor. Then you'll be like, sir, the same thing should happen for a conductor also. For a conductor also, if I increase the temperature, conduction should increase and resistance should decrease. No. Reason? There are already enough electrons in the conduction band. It's already crowded because of the free pass between these two bands. So when it is already crowded and when you increase the temperature, the crowding effect with the thermal energy makes it worse. So these electrons start to move with a lot of energy. There is hardly any space for them. In fact, that crowding with that craziness, with that energy leads to increase in the resistance. So that's why for conductors, the resistance will increase when temperature is increased. Very, very important. Okay. So very important points. It's again going to be available to you in the PDF. Let's see how many of you can solve this question coming up on your screen now. Excited, my warriors, to solve the questions? Get ready. Which of the following is correct? Okay. Actually, this is a multiple choice. More than one may be correct. Let's see how many of you can mark this. Come on. Done. Forbidden energy gap is the energy gap between the two valence band and the conduction band. Between the valence band and the conduction band, forbidden gap may be empty or may be partially filled with electrons. No electron will exist in the energy gap. Bands cannot overlap with each other. I think this is straightforward from theory. Option A and option C obviously will be correct. Reason being, forbidden energy gap is the energy gap between the valence band and the conduction band. Yes, that's true. There can be electrons in it. No electron will exist in the forbidden gap. That's true. And bands can overlap with each other. I just shown this to you right over here. This is your forbidden gap. Either the electron can be over here or here, not here. Number one. This is the energy difference between your conduction and the valence band. And they can also overlap with each other, just like over here in the case of conductors. You can see the overlap. The shaded part is the overlapping. So it can also overlap. Hence, the correct answers are option A and C. I hope you got it correct. If you got it correct, show a smiley face. Some of you are probably hesitant to chat. Don't feel nervous. It's okay even if you are wrong. Trust me, I still love you. I still care for you and I'm still going to support you. We are all learners. You are all students. And the job of a student, one of the duty is to make mistakes. If you are a student who is not making mistakes, then you are not learning. You are missing something in life. A semiconductor close to 0 Kelvin behaves like insulator, conductors, semiconductors, superconductors. Okay. Super semiconductors is just there to confuse you. This is very obvious now. 0 Kelvin, that means very low thermal energy. The electrons will not be able to jump because of the lack of the excitation provided by the temperature. So the electrons will not be able to jump to conduction, they will remain in the valence band, and hence the answer will be insulators. The electrons can't jump from the valence to the conduction band. I hope you remember, I just gave you, if this is your valence band and this is your conduction band, for making that jump happens due to the thermal energy. If there is no energy, then obviously all the electrons are just going to stay here only. They are not going to make that jump. And you will see vacancies right over here. Got it? So very important, semiconductors are insulators at low temperature. Semiconductors are insulators at low temperature. This was asked in one of the JEE examinations. So cool, right? Okay, let's move ahead to the next one. Get ready. Okay, so a lot of problems going to come up after this as well. Now, remember I gave you the chart where a semiconductor can be of two types, intrinsic, extrinsic also of two types. Let's discuss that. Only then we can go to PN junction diode, all of this. So, intrinsic, internal. These semiconductors are pure semiconductors. There is no adulteration, there is no mixing. It's just pure semiconductors, and they have some decent amount of conductivity, not as good as a conductor, but not as bad as an insulator like paper or wood. Best example, germanium, silicon. These are very, very good examples of, intrinsic semiconductors. And you will see something called as holes and electrons being formed in these kind of semiconductors. Now, what are these holes and what are these electrons pairs which are formed in any kind of semiconductor? This is very, very important. Let's talk about it. First of all, let's say you take any, let's say silicon, or I don't know, any kind of semiconductor. Let's say for example silicon, and each silicon atom will bind with 4 more silicon atoms in its vicinity, something like this. So these are the silicon, it could be germanium, anything. Each silicon atom will contribute 1 electron, and this will contribute 1 electron. They will form bonds with the neighbors. It's not a double bond. Each line, okay, don't get confused. Each line represents, the contribution of electrons. Okay, as such, it's just 1 bond, and so on and so forth, and it will obviously extend till as large the solid is. Okay, these are the electron sharings which are happening in that vicinity. Fair enough. Now, remember, at room temperature, because the whole game is at room temperature, you're not going to have semiconductors at 0 Kelvin, because then it's of no use. Semiconductors are useful when it is at room temperature or close to our day-to-day temperatures. What happens is that at regular temperatures, there is shaking, there is vibration, there is thermal energy. And what will this thermal energy do? It's bad for these atoms' bonds, because these atoms will move. And when these atoms move, shake, twist, their bonds can be broken. What happens? The bonds can be broken. So say for example, there are 2 such silicon atoms whose bond is broken due to movement because of thermal energy. So this thermal energy, I have mentioned it right over here. Thermal energy might lead to the breakage of bond. Okay, so I can mention this over here. Bond broken, okay, due to thermal activity, or energy. Now, the moment the bond is broken, okay, you will have one electron which is free, and one vacancy created over here. You will immediately have one vacancy. This is your vacancy which is created over here. Okay, vacancy which is created over here. Similarly, there might be many more such vacancies created due to breakage of bonds. Maybe another bond was broken, I don't know, maybe let's say here. So due to the breakage of bonds, again you might have some electron which has been released, and also you might have another vacancy which is created right over here. Now what will these electrons do? Because they have been knocked out by those thermal energies or excitations, they will have kinetic energy and they will move around. They might collide, they might interact with many things, either the atoms, the bonds, the electrons. There are so many options. One such option is, as they keep on bouncing around and they keep interacting, they might happen to come across some hole. Remember, hole is a vacancy. It's like, hey, I'm here, please come on, there's a job vacant out here. And these electrons, they are like job applicants looking for job. They are going from door to door, from company to company. Oh, give me a job, oh, give me a job, oh, give me a job, oh, give me a job. And these holes are like, hey, job openings are here, hey, job openings are here, something like that. So if that electron just happens to, come across one such hole, then it will immediately fill it up. So probably it might fill the hole. This vacancy, by the way, is called as a hole. This vacancy is called as a hole. And you can see in this entire process, the electron, the negative charge, has gone from here to here. The electron has gone from here to here. The vacancy has shifted from here to here. Think about it logically. The electron, the negative went from here to here. The vacancy went from here to here. Vacancy is the lack of an electron. You can think of it like a positive charge, but it is not a charge. Please understand, there is difference between a positive charge and a hole. Lot of people think, sir, hole is positive charge. No, hole is not a positive charge. It's like a positive charge. It's the absence of an electron, vacancy which is created. So you can see if electron goes here, the hole moves over here. I hope this makes sense. And this will be happening everywhere randomly. Electron jumping from here to here, hole jumping from here to here, electron jumping from here to here, hole jumping from here to here. So on an average, when all these jumps happen, what will be the net flow of charges? Answer in the chat box. What do you think will be the net flow of charges due to all these jumps happening everywhere? Obviously, it should be zero. If some electron has gone from here to here, sometime some electron will jump from here to here. If some hole has gone from here to here, some hole somewhere will jump from here to here. On an average, everything will cancel out. Everything will cancel out. Is that making sense to all of you? Is that making some kind of, sense of, is it giving you some kind of feeling of what is happening inside a semiconductor? So many jumps happening around it. Great. Now, the flow of current happens because of these jumps. The flow of current happens because of these jumps. So when you connect a battery from outside, let's say for example, this is your semiconductor. Okay, it could be anything. This is your semiconductor. All right. And let's say you connect it to some battery. Okay, say for example like this. You connect it to some battery like this. What will happen is this is at high voltage, and this is at low voltage. Okay, so what you're going to see, there will be electric field which will be set up. There will be electric field which will be set up like this. And what will happen because of this electric field? Charges which are there, electrons which are there. Where will the electrons go? Electrons will get applied by a force opposite to the field. So you will see the electrons moving like this, and you will see the holes because of that shifting like that. So the holes will move like this. So guys, answer a simple thing. If electrons go like that, holes go like that, the total current will be cancelled? Will the net current be 0? Electron going like that, hole going like that, will the net current be 0? No, this is where many students make a mistake. Guys, if an electron goes like this, it's as good as saying the positive charge is going like that. Think about it. So, due to the electron, you will see the current due to the electron in this form. Remember, current is the flow of positive charge, conventional current. So if electron goes like this, current is going like that due to the electron. And hole, anyways, it's absence of an electron, which is like a positive charge but not exactly a positive charge. So the current due to the hole is like this. So due to the holes moving, the vacancy is going like that, the current due to the holes is like that. Hence, you will see that together, the net current is basically the whole current plus the current due to the electron. So that's what is very, very important. It is not minus, it is plus. Get this right in your head. Very important relationship, very important equation. Okay, both of them will add, it will not subtract. Keep this in mind. Okay, usually the current due to the hole is less because holes can't move so easily, because holes are vacancies. Electrons can jump very easily from one to other. So usually, most of the times, electrons current is more as compared to hole current, usually. Okay, keep this in mind, usually. Is that understood, my warriors? Fair enough? Clear? Concepts are clear? Put up a heart. Yeah, put up a yo. Come on, keep the chat box lit. Hey, very good. Let's move now to the next part. See, we started right from basics, right? Sodium atom energy levels, combining energy gaps, energy bands, and then overlapping, not overlapping, creating semiconductors. Now we have gone to what is an intrinsic semiconductors and how the current flows in an intrinsic semiconductor via holes and electrons. Now what is an extrinsic? Imagine you create some adulteration, you add something so that the conduction properties change. You can see some more currents due to some kind of adulteration. That is called as an extrinsic semiconductor. You add some kind of adulteration or impurity, or you dope it. Doping it, adding impurity or adulterating, it's one and the same thing. Now, how do you make it more conductive? There are two options. Number one, you add more electrons, so which will contribute to the current. So how do you increase the conduction? Either you add more electrons and increase the current due to the electrons, or you add more holes and increase the current of the holes. That's another way. So that's why you have P and N type of semiconductors. Okay, are you getting the hang of it? Stay with me till the end. Trust me, you will understand this topic. Many students don't understand this topic, and that's why you find this chapter theoretical or boring, or you just leave it as an option. Trust me, if you understand it, you will get it. Okay, so we are going to see N type as well as P type. N negative, more electrons. P more holes, positive. So two kinds of impurities can be added. One is a pentavalent, other one is a trivalent kind of impurity to any kind of semiconductor. So you take any semiconductor and you can add some pentavalent. Pentavalent means 5 electrons. So one electron is excess, because silicon will have only 4 electrons in the outermost shell. So one electron excess is available. So that will contribute in the conduction. And in trivalent, which you're going to see over here, it has one less electron which will contribute to the whole. So let's have a look at it. Pentavalent, it could be like phosphorus, it could be anything. Pentavalent will have an extra electron, and this extra electron will not bind with anything. So for example, look at it. If this was our, let's say, silicon, then let's say you have phosphorus or something like that. Okay, you have silicon. Okay, so this extends till infinity, of course. Now imagine if it's a pentavalent, what will happen? You will see one more extra electron over here. If you add more such pentavalent impurities, there will be so many electrons, so many places. Those electrons help in contributing to the extra current, and that's why the conduction changes. Now if you look at it, yeah, so you can see over here, this is N type of semiconductor like germanium doped with As out here, okay, arsenic, and you can see energy wise what happens is that when you add an N type of semiconductor, remember our usual band gaps used to look something like this. This was your conduction band, this was your valence band, and this energy gap was approximately 1 electron volt, if you remember, for a semiconductor. This is for intrinsic. This is for intrinsic. Now what you are doing is that you are adding 1 electron over here, that impurity. So because of that, a new band is created right over here. A new band because of that N type of impurity. So what happens is, in the earlier case, the electrons had to jump from here to here. That was a much wider jump, bigger jump by the thermal energy. This was big jump for intrinsic. But the moment you create an N-type impurity and you add it over there, then you will see the jump for this electron from here to here is much smaller. So that's the reason why the conduction increases. So the energy gap actually shortens because of an extra layer of that N kind of electrons out there. Okay, that new energy level being created over there. Okay, is that clear, my warriors? Energy wise, that's what happens. So you can see the gap was big. Now you have created an N-type impurity over here, so the gap has reduced, so increases the conductivity. Fair enough. Now in a P-type, what will happen? Vacancy. Vacancy means hole. So that extra hole contributes to the current. So that is called as a P-type of semiconductor. Usually it is a trivalent impurity. And look at this out here. There is a vacancy which is created. Usually all the germanium atoms, they are bonding by contributing one electron each with their neighbors. Here there is one hole. I hope you can see that. There is one vacancy. Okay, there is one hole which is created extra. This is an extra hole created due to this trivalent impurity. Now what happens is, just go back to our previous energy level diagram. You had conduction band and you had your valence band. So usually for an intrinsic semiconductor, the electrons had to jump from here to here, right? This was for your intrinsic semiconductor. The moment you create it as a P-type semiconductor, what happens is you create a new P-type vacancy. This is not filled, this is vacant. This is P-type. P-type. It's vacant. I'm not shading it. So the empty shells come down. So instead of jumping from here to here, now even if it jumps from here to here, it is okay. This is for the P-type. So you can see the effective band gap has reduced. So what happened in N-type? In N-type, you increase the valence band's energy effectively so that the jump was less. So you gave it a platform so that, okay, instead of jumping this much, now you take this stool and now you jump. So that's what an N-type is. But in P-type, what is it? In P-type, it's like, okay, you don't jump till there, you just jump till here. That's fine. So either ways, you are increasing the conductivity. Fair enough, my warriors. Everyone clear till this point? Shall we go ahead? Interesting topic, right? How many of you are finding this interesting? How many of you are finding this very, very different, very, very, unique kind of a theory chapter? where there is so much of logical thinking into it. Okay, and that's what your devices, your memories, your logic gates, everything are based on these semiconductors, and they all play around at atomic level. Crazy. So let's talk about the important formula for conduction of electricity in semiconductors, be it N type or P type. It's a very, very important formula. Now remember one thing, okay, just before going over here, yes, let me just add one more note. See, in just one second, in N type you need to remember one more thing, because you are adding impurities, the electron concentration increases. So if I tell you a number Ne, which talks about the electron concentration per unit volume, and if I talk about another number NH, which is the whole concentration per unit volume, because of those excess electrons, you can see that right over here, this is that excess electrons, okay, the electron concentration is much higher than the whole concentration. So when you dope it, you are adding a lot of phosphorus atoms or pentavalent impurities, the electron concentration increases as compared to the whole. But for what is this, intrinsic semiconductors, keep this in mind, the amount of electron concentration is equal to the amount of hole concentration, which is often called as Ni. I stands for intrinsic. I stands for intrinsic. Keep this in mind. Okay? Okay, fair enough. Now, similarly, in P type of semiconductor, going back over here, so in P type of semiconductor, what you will see, the amount of electron concentration is less than the amount of hole concentration. Keep all these things in mind, very, very crucial. Now, there is a relationship between all these quantities. So, what is the relationship? If Ne and NH represent the electron and hole concentration respectively, very important line over here, they represent electron and hole concentrations. So it's basically number per unit volume. Then it so happens, this formula is always valid, keep this in mind, number of electron concentration, number of hole concentration, the product of that is always number of intrinsic semiconductors concentrations square. So this is the formula, keep this in mind. Ni is the intrinsic carriers concentration. I just gave that to you some time back. So this is Ni. Okay, keep this in mind. Okay, if this increases, this decreases, that increases, this decreases. Okay, so that's how they work. Keep this in mind. All right, cool. Another important formula which you should know, very, very important, called as the mobility and conduction formula for semiconductors. There were times when JEE has asked, and even boards has asked questions based on this. I'll tell you what it means. See, let's derive it. In fact, that will be better. Okay, we want to find what is the conduction of, or the conductivity of a semiconductor, be it N type, be it P type, be it intrinsic, the conductivity of a semiconductor. Now, how do I do that? Let's go by basic formula. Conductivity is 1 by resistivity. Fair enough? Okay. How is resistivity related to anything else? I think I know it. So we all know that E is equal to rho J. Everybody might have seen this formula. V is IR, similarly E is a rho J. So therefore 1 by rho comes down, will be J by E. Correct? Hence, from this and this, I will get J by E is nothing but sigma. So this is sigma right from here, correct? Fair enough. Now what is J by E? Well, let's think, what can we do for J? I think I know one formula for that, and that is, since I is equal to N drift speed EA, I is equal to NVIDIA, therefore J, which is I by A, will be N Vd into E. Hence, I can substitute that over here and see what do I get. Sigma is equal to, instead of J, you put N Vd into E, and that E comes over here as it is. Fair enough till this point? Great. Now this number, drift speed by electric field, is called as a new quantity called as the mobility. I might have spoken about this even in current electricity if you were there during that time. So I'm just going to write this down as, therefore, sigma is equal to N mu into E. Very important formula, where mobility is nothing but mu, which is drift speed divided by electric field. It tells you how much speed do these carriers, charge carriers, have per unit field. If I apply some electric field, how fast they can move, how mobile they are. That is mobility. That's what it says. N is how many carriers are there per unit volume. And E is your charge. So that is your conductivity. Okay, so that gives you your conductivity. But this is not the entire formula. Reason, remember, the conductivity or the conduction in a semiconductor happens because of two things: current due to electrons and current due to holes. That means the conduction due to electrons and holes together will give rise to the net conductivity of the semiconductor. Hence, the final formula is sigma of any kind of semiconductor is sigma due to electron, sigma due to hole. Therefore, sigma of any kind of semiconductor is, just substitute these values just 2 times. Okay, just 1 second, let me get some space over here. Okay, so this will be N as in electron concentration, mu as in mobility of electrons, E is the charge of the electrons, which is E itself, plus sigma for holes, number of hole concentration, into mu for holes mobility, into charge of hole will also be E. Hole is absence of an electron, that means plus E charge. Hence, this becomes your final formula. Very, very important. Keep this in mind. Okay, sigma of this plus sigma of that. Is that clear, my warriors? Okay, very, very important formulas that you have learnt. And remember the relationship between Ne and NH? I just gave it to you in the previous slide. Ne and NH product is Ni square. Okay, and in N type, Ne is more, lot more. In P type, NH is too much, and in intrinsic, both of them are equal. Okay, that's how it works. The product of their concentrations always remain constant. Fair enough. Let's go with some questions now. Get ready with your pen and paper. Ready to solve some questions? Give me a thumbs up. Yep, ready? Okay, let's start. Here's the first question coming up on your screen. In a pure silicon, Ni, which is 10 to the power 16, okay, per meter cube, it should be cube, the crystal at 300 Kelvin, 10 to the power 21 atoms of phosphorus are added per cubic meter, then the new hole concentration will be. Interesting. Now Ni, this one is basically your intrinsic concentration. This phosphorus is a pentavalent impurity. That means this number over here per unit volume, that is your Ne concentration. What is asked? The whole concentration. So what is asked over here is what is NH. Now I know which formula to use. Obviously, Ne into NH is equal to Ni square. Ne from there is 10 to the power 21. into NH, I don't know, is equal to Ni is 10 to the power 16 whole square. So therefore NH will be 10 to the power 16 raised to 16 whole raised to 2 will be 10 raised to 32, and this is 21. So that's it, it comes below. So therefore NH will be 10 raised to 11. Is it there somewhere? Yes, I suppose option C. Isn't it simple? If you get such kind of a question, do you want to leave it? These are bonus, like free available marks served to you in platter. It's just a matter of, can you watch this lecture and can you understand it, go back and solve the homework and also solve the assignments, everything. That's it. Trust me, your job is done. Within one day, one question you have secured in your pocket. That's how you secure each question day by day. It's not going to happen overnight. You have to work every day to secure 4 marks. If you think, you can get 100 marks in or 50 marks in just watching one lecture, that's not possible. You have to build it up slowly and you have time. Okay, moving on to the next question, see what's correct. The contribution of the total current flowing in the semiconductor due to electron and hole is this. If the drift speed is 5/2 times that of hole, then the ratio of the concentration of the electron and the hole is. It's a question on drift speed. So I think I will stick to the drift speed formula. The drift speed formula is I is equal to NVIDIA. Interesting. So think about it. The question is all about electron and hole. So the current due to electron and current due to hole. It's mentioned. I due to electron, I due to hole. It's given. Drift speed is also given as a ratio. And the question is, what's the concentration? N. So I think let's take the ratio first. Probably that will eliminate few of the things. So I by IH will be NE by NH into drift speed of electron upon drift speed of hole into electron charge upon hole charge, which is the same. Area is obviously the same. E and A gets cancelled. I just have these two terms left. Now it's just a matter of substitution. Current due to electron is mentioned. Due to electron and hole. So this is due to electron. It's 3/4. Due to hole, it is 1/4. NE by NH, I do not know. In fact, that's what I need to find. The ratio of the concentration of the electrons and holes. So this entire statement, this statement just means what is NE by NH. That's the reason why I have taken the ratio of electrons and holes current. Is that clear? Shall we go ahead? Okay. What is this then? Let's think about it. Drift speed of electron is 5/2 times that of holes. That means this number is 5/2. Okay, and this number just became 1 into 1. So therefore, NE by NH will be 4 goes. Okay, NE by NH will be 3, and that 2 comes on the top, and that 5 goes below. So that will be 6 divided by 5, and I have it over here as option number 1. That's it. It's simple, nothing great, just formulas. Simple. Easy peasy lemon squeezy. Can we go ahead? Okay, have you squeezed the lemon? Shall we go ahead, my warriors? Perfecto. Keep the chat box lit. Yep. Don't let your energy die down. Remember, your energy will motivate others. And it's a good thing to motivate others. That's what true warriors do. Okay, so go ahead, put up your answers irrespective of what you think is correct or wrong. Next question. There is an N type of semiconductor. And what do we have? The density of the electrons is this much and their mobility is this much. Then the resistivity of the semiconductor is close to. Let's see, resistivity has been asked, mobility is given, and concentration is given. Is there a formula somewhat which is relating all these three things? I think so. Sigma is for an N-type semiconductor. Okay, is nothing but, think about it, N, mu and E. But due to both of them, like electrons and holes. Now I can see only electron concentration is mentioned. What about hole? Okay, let's think about it. All this is for electron. Similarly, I'll have one more term exactly like this, n mu e, but that's for hole. Now the thing to keep in mind is this is n type of semiconductor. That's what changes everything. In n type, the number of electron concentration is much larger than the hole concentration. Probably we have to make an assumption. That's why this has been written in the question, close to. That means you have to approximate. So how do I approximate? If electron concentration is more than the hole concentration, that means these terms will be higher than these terms. In fact, even the mobility of electron is much higher than that of hole. Correct? Electrons are more mobile, holes move slowly. So this term is much higher. So this is larger than this. Very important. So I can neglect it. And the moment I neglect it, things become very easy. Sigma, therefore sigma approximately becomes n e mu e into e. And sigma and resistivity, I know resistivity is 1 by sigma, therefore it is 1 by n e mu e into e. What has been asked? The question is the resistivity. All right, let's start substituting everything. So what do we have over here? Number of electron carriers, that's 10 to the power 19 into mu, mobility is given as 1.6. Okay, and electron charge, that's 1.6 into 10 to the power minus 19. This and this vanish. 1.6 into 1.6, 16 square, 256. So this will become 1 by 2.56. 1 by 2.56, and it's asked close to. It's, can I say give or take? Give or take. This is roughly 1 by 2.5. So just put one more 0 here. So you'll have to put 10 over here. 10 by 2.5, that's 4, right? This is 10, right? This is 10. So which is approximately 0.4. Can I do that approximation? Did you understand what I just did? 1 by 2.56 is 1 by 2.5 roughly. Multiply by 10, divide by 10. 10 by 2.5 is 4. And this 10 and this 4.4. Okay, so this value should be very close to 0.4 ohm meter. That's the resistivity unit. So that's the final answer. Let's see whether it's correct. Yes, it is. It is 0.4 ohm meter. Okay, so very straightforward, logical, some approximations, and all of this you know only because you have been in this class right from beginning. And if you are joining in a little bit late, please rewind back the session and watch it from the beginning. Do not skip any part. This will for sure give you those 4 marks in JEE Mains. And if you're loving this channel, if you're loving this video, if you're loving all my explanations, please go ahead and hit that like button for all the efforts that I'm putting for all of you. Okay, let's talk about now PN junction. So you take the P type and N type and bring them close to each other. What happens is a miracle. You might be thinking P positive, N negative. No, P is not positive. P is just the lack of electrons and N is just excess electrons. But do not forget, when in an N type there is an extra electron, there is also an extra proton inside the nucleus. Still N type is neutral. A lot of people think N type is negatively charged. That's so wrong on all the levels. N type is just having an extra electron which cannot form a bond. But at the same time, there is extra proton in the phosphorus pentavalent impurity. So it balances out, neutral. Similarly, P type has one less electron and there is also one less proton inside the nucleus. So it is still electrically neutral. How many of you did not know this before? Did you guys now get it? Very good. Now, going ahead, when you bring them together, that's when the N, which is in search of electrons, and the P, which is like holding the placard and saying, hey, all those people who want jobs, job vacancies, they are like holding the postcards. And electrons looking for jobs. Where are the jobs? Looking out for holes. They see each other and they are going to attack onto them. The electrons will jump onto the holes. That's what a p-n junction. Junction means they meet. And that forms something called as a p-n junction diode. You'll be like, sir, what is this new word, the diode? Okay, I'll tell you what this diode is, and I'll tell you in the next few slides why p-n junction is a diode. Okay, we'll understand it. Diode simply means in unidirectional. Unidirectional. Now, the best example that I can think of is the vessels inside your body near the heart. There are some vessels which are supposed to make sure that the blood enters only inside the heart, and some vessels which have to make sure that the blood exactly comes out of the heart. So these walls which are there, they are unidirectional. So they only allow the flow in one direction. If it tries to come back, it blocks. So same way, in a p-n junction diode, you will see the current can only flow in one direction. If it tries to come back, it's like, no, sorry boss, one way traffic. You cannot break the rules. Sorry, go back. So that's a diode. Now, why does a p-n junction behave like a diode? You will understand it. Now, first of all, let's understand what exactly happens when you bring these p and n wafers together. So p side and n side. This n side has lot of electrons, p side has lot of holes. Okay, one more misconception which people have. P will only have holes. That is also wrong. Do you forget that there is thermal energy and there are always bonds which are broken? Lot of bonds are broken. So because of which there is always one electron and one hole which is created. So most of the things on p side are holes, but there are some electrons. Didn't I just give that to you in p and n type? NH is much larger than Ne, and in n type Ne is much larger than NH. But NH is there and NH is also here. Okay, Ne is also there, NH is also here. So understand, there are some minor charge carriers in p type as well as n type. So majority charge carriers in p type. What are the majority charge carriers? Let's write it down over here. Okay, keep this in mind. Over here, majority charge carriers. What are they? Basically holes. And here in n type, majority is what? Electrons. Same way, I can also talk about the minority. You can see that right over here. Minority is nothing but your electrons, and the same way over here, the minority is nothing but the holes. Okay, very few of them. Now one can easily see that these electrons will immediately jump from here to here, here to here, here to here. There could be few electrons which jump there, but obviously most of them are going to jump from the n side to the p side. They are going to conquer it. Now the moment they jump, things change drastically, and that's what I want you to understand. Okay, so let's just make this diagram just for your sake. Okay, let's say over here, these are your electrons. Okay, lot of electrons are there. I'm just showing it over here. This is your n side, and over here, there you go, you have lot of holes. Well, I hope this color is visible, and the good thing of PowerPoint is you can have a lot of colors. Okay, so this is the p side. Fair enough. Now borders, what will happen is these electrons are going to jump over here. Remember one thing, that n and p were actually neutral before these jumps. So I'll mention that point over here. N and p, when isolated, are electrically neutral. But the moment they are in a p-n junction, you will see the electrons jump from here to here. When the electrons jump from here to here, what will happen? The P will become negatively charged and N will become positively charged. This is something which you should realize. N does not become negative, N becomes positive because the electrons leave them. And P will become negatively charged because the electrons actually jump over there. Very, very crucial. Getting it? Everybody with me on this? Come on, light up the chat box. Fair enough. Now, the moment they jump, let's put the charges out here. Okay, you will see negative charges over here. Can you see the negative buildup and positive charges over here? Just like I've shown over here. Because of that, there is a field which is created. So hence, I will say that there is a electric field which is created. And what will a field do? It will create a force. On whom? The charges. So once the positive charge is built up and negative charge is built up over here, field is here, that means force on the electrons will be that side. The force on the electrons will be towards this side, right? Because electron is negatively charged. So do you think these electrons will find it easy to jump from here to here? Yes or no? Earlier the electrons did not face any problem because this was not charged. But the moment they jumped, this became positive, this became negative. So negative and positive will create an electric field, positive to negative. That will create a force, negative to positive. That force will prevent the further jump of electrons. What will this do? Okay, what will this do? Prevents the further jump of electrons. Very, very important. Fair enough. Because of which you will not see all the electrons going and settling here. These people will act like a barrier. They will stop the flow of the electrons. Now this process of the electrons jumping from here to here, that is called as diffusion. Diffuse. Imagine there are two chambers. One has hydrogen, one has oxygen. When you open the partition between the two chambers, hydrogen goes over there, oxygen goes over there, they'll mix. So the moment you open the barrier and basically you bring those P and N type together, these electrons jump here, holes go there. So they mix. Mix is diffusion. That's why this kind of movement is called as diffusion. And the current which arises because of this is called as diffusion current. The current which arises because of this is called as diffusion current. Everybody clear? So which direction do you think the diffusion current will be? If electrons are going from here to here, they are completely migrating, all right? All these electrons migrated. So which side will the diffusion current be? Think about it. Think about it. So this is the diffusion. This is the diffusion of electrons. Electron is negatively charged. Hence, the diffusion current will be this side. So I diffusion will be towards this side, from the P side to the N side. Got it? No battery has been connected, nothing has been connected, just the electrons have migrated. Also, okay, I can show this to you in energy level diagrams. This is majority charge carriers N type, this was P type. You will see that there is some energy difference and some of the electrons are going to migrate from here to here the moment you bring them close. You saw that? Okay, some of the electrons have migrated. You see that? And they will satisfy the holes, obviously. Something like this. The electrons migrate, they satisfy the holes, and because of that, you will see that there is some, barrier which is created. Why is that barrier created? Because of the field. Remember, there was an electric field which was created, so it will create a barrier. Okay, so you can see that simulation once more so that you get a hang of it. Electrons migrated from N to P type. They will satisfy the holes. Okay, and the moment this happens, this becomes negative charge, this becomes positive charge. Electric field creates the potential difference. This is the barrier. This is the barrier. Okay, So this red line over here, if you're wondering what that was nothing but your potential difference. Electric field always goes from high potential to low potential. So this is at high potential, this is at low potential. So that potential difference is called as the barrier potential. Very, very important. This barrier potential delta V will be electric field into delta R. What is this delta R? This is the width. This is the width of that barrier. This is the width of the barrier. Width of the barrier. Okay. So that is how it works. And I just mentioned to you what diffusion current is just some time back. Diffusion current happens when electrons from n-type diffuse into p-type. That creates a flux of electrons which creates a current in the opposite direction. Okay, fair enough till this point? Cool? Now, this is not all that happens. There are more things which happen. Now there is something called as drift also. Because how can electrons just keep on moving from here to here? If there is a current created and if there is nothing connected, battery, nothing, there must be something to oppose it also, right? And that is drift current. Okay. Now, what is this drift current? There is a positive charge here, there is a negative charge here. Because the electrons migrated, the electrons have migrated, that means diffused from the n-type to p-type. Now, in this region, this is the depletion region, the barrier region, the depletion. They have been depleted. In that region, what happens is, just imagine, there could be, okay, in that region, this is silicon, maybe, I don't know, silicon, something like that. Okay, and more such things. This is n-type, right? So let's say phosphorus. Okay, and let's say here something like aluminum, trivalent impurity. Okay, something like that. Okay, fair enough. So you can clearly see that this side is your p side, and this side over there was your n-type. Okay, this is your n-type, and this was your p-type. Now imagine I am talking about the depletion zone. This is your depletion zone or depletion layer, which has been formed between that barrier, positive charge, negative charge. That field is there here. Remember that field exists from positive to negative. Okay, I hope you remember that. So there is a field in this region. So that field, okay, I'll just put it in some different color. So that electric field is here. That electric field is here. Hence, the force on the electrons, is on this side. Now, think, there will be some shaky movement. There will be some thermal energy, which is still there, correct? Even in the depletion zone, some or the other bond will be broken. Makes sense due to thermal energy. So the moment any of the bond gets broken over here, you will see that one electron is created and obviously one hole is also created. Why has this happened? This has happened due to your regular thermal excitation. Now think what will happen. This electron has been caught between the battle of n and p type, where this was positive, this was negative, there was electric field, there was force. So there will be a force on the electron. Where will that electron move? The electron will go here. Look at this. This electron will now start going here. It will do something called as the drift. Tokyo drift, this is electron drift. And the hole, what will the hole do? The hole, this is your electron drift, this is your hole drift. So because of this, where will be the current? Think about it. Electron goes here, hole goes there, electron is negative, so current is that side. Hole is positive, still the current is that side. Hence, you are going to find a new current like this. This will be the drift current. If drift current is like this, your diffusion current, or diffusion was happening this way, right? So the diffusion current was the other way. Diffusion current will be this way, and they will balance out each other. This is like a dynamic equilibrium. Okay, got it? And so there is no net charge movement. Net current is zero. Very, very important. So diffusion happens because of difference in concentration, N to P type. N to P, electrons diffuse. They create barrier, depletion zone. There is field inside the depletion zone. Any new bonds which are broken in the depletion zone, those electrons are now going to experience the force due to that field. So these electrons will move exactly the opposite way of the diffused electrons, and that creates drift current, which will cancel it out. That's what happens. It's crazy. Okay. Oops, I think I just probably wrote everything over here. No issues. I will probably create another slide before giving this to you. Okay. Fair enough. Let's start solving some questions. There is a potential barrier of 0.5 volts which exists across a PN junction. If the depletion region is this much wide, then the intensity of the field in this region is how much? Come on, this is not even a question of semiconductors. This is something which you would know even without the knowledge of semiconductors. Barrier is given, the width is given. The question is find the field. Isn't the field E is del V by del R magnitude wise? The negative sign signifies the direction, but magnitude wise, this is the formula. Del V, potential difference is 0.5. Del R, what is the del R? It is 5 into 10 to the power minus 7. So what is this? 5 into 10 to the power minus 1 upon 5 into 10 to the power minus 7. So this will become 10 to the power minus 6. That's it. Do I have 10 to the power, plus 6, my bad. 10 to the power plus 6 somewhere over here? Yes, I think I have it. 10 to the power plus 6. That's the answer. Option A. Simple. Super duper, lemon squeezy, easy peasy. Very good. Let's move to the next one. Which current does depend on the minority charge carriers? Minority. The charges which are in minor number. Minority charge carriers. Come on, guys. If you remember correctly, I had told you before starting of PN junction, there are some minority charge carriers everywhere. Why do these minority charge carriers come? Because of thermal excitation. And which current depends on the thermal excitation? I just gave it to you. Thermal energies, excitation breaks the bonds, creates new charges. Be it N-type, be it P-type, there are electrons and holes. Doesn't matter, due to the thermal excitation. And that is your minority charge carrier. So that was your drift current, and hence the answer should be option A, drift. Got it? Wow, what a fabulous lecture. I hope you are loving it now. Okay, let's move on to the next question. But before that, let's talk about the two biases that we have. Okay, not much is remaining. Let's quickly go ahead. Biases. Two types of biases are there, forward and reverse bias. Very, very important. So guys, forward bias means you are conducting the flow of the charges by connecting the P type to positive, N type to negative. The electrons from N to P move, diffuse. What if you pull these electrons further by connecting it to a positive terminal of a battery? So all these electrons will get pulled and the negative terminal repels these electrons. That's why you will see there will be a flow of charges in the circuit. That's why it is called forward biasing. The electrons want to diffuse over here, and you're pulling these electrons further by connecting it to positive, and you're pushing these electrons by repelling them from this side. That's your forward bias. Okay, and when this happens, you will see the width of this barrier decreases. You can see that energy wise. So when you push it from N side, okay, you're pumping it, you're pumping up the energy, you're decreasing the barrier's height. So the electrons will be easily able to go onto this side. They will just keep falling because the barrier has decreased, and you will see the conduction starts. So that is forward bias. Very, very interesting diagram. Okay, you're pumping it up, you're reducing the energy difference. Whereas in reverse bias, you will see you are going to connect the P to the negative terminal and the N to the positive terminal. Because of this, what happens? The electrons will get pulled towards the positive terminal and the holes will get pulled towards the negative terminal. In fact, this negative terminal will prevent the flow of influx of the electrons from N to P type. So you will see the width of the depletion layer increases and you will hardly see any current flowing in the circuit. So there will be no diffusion which will be happening in the circuit because there will be hardly any electrons to propagate. So that's what is reverse bias, and the only current which will be flowing will be very, very minute. That will be because of the minority carriers. Majority of them will not be flowing. That is your reverse bias. You are stopping the current. It won't flow only because electrons wanted to go here and go like this. This negative terminal will be like, stop, I'm repulsive. So the electrons will get pushed back. In fact, they will also get pulled by the positive terminal. Is that making sense? Okay. So you can see in this case the energy gap increases. In fact, there is no animation that I can show because none of these electrons will be able to make it here. It has to climb this up. In the previous P type, if you notice, this width was decreased, so they could easily go into the conduction band and they could conduct the electricity. So here there will be no conduction of electricity. Got it? Very good. Now the most important thing right over here, very, very important, is that how does the graph of voltage versus current look like? It looks something like this. In the forward bias, when you increase the voltage, you will see the current increases because the conduction begins. In the reverse bias, no matter how much voltage you apply, it will not conduct. Yes, there comes a point where it starts conducting, but that is too late. I mean, that is called as a breakdown. It gets broken down completely. That is the reverse voltage, reverse breakdown voltage. But usually you will see that the graph is of conduction only in the forward bias. When you apply some voltage, you will see the current changing. Now here is something which is very important. For a normal conductor, voltage was proportional to the current. Here it is not. So that's very, very important for you guys to see. Voltage is not proportional to the current. So resistance, which is V by I, is definitely not constant. Very, very important. Okay, resistance of a semiconductor is not constant. That's what I was telling you. It depends on the voltage. More the voltage you apply, the more the electrons get pulled, the forward bias conduction starts. And it is a very random non-linear graph. Also, one more important thing is that when you draw a tangent to this and you measure the slope, which will give you delta I and delta V, then when you find this value, R is equal to delta V by delta I, this R is not your usual resistance because the resistance is just voltage by current. Delta V by delta R, this is called as your dynamic resistance. What is it called? Dynamic resistance, del V by del I. Just V by I, just your normal resistance, also called as your static resistance. Static resistance, as simple as that. Okay, now you would have understood looking at this graph that the current inside the diode only flows in one direction. It does not flow in the other direction. That's very interesting. It only flows in one direction, it does not flow in the other direction. So it is like a valve. It can conduct electricity only in one direction, in other direction it can't. So that is the reason why it is called as a diode. And this is how a small PN junction diode looks like. This is a magnified image. It's hardly this much. It's so small. It's a diode because it's like a wall, because it can only conduct electricity in one direction. Look at the symbol of a diode. Very, very important. You draw a triangle and a line. This is the P side, this is the N side. PN junction diode. Now does the name make sense? Does it make you believe, or does it give you the feeling that yeah, now a PN junction like a diode? By just looking at this IV characteristic graph. Conducts here, does not conduct here. Very, very important. This is a symbol. You should know this. Okay? Cool. Let's solve some questions. The dominant mechanism for motion of charge carriers in forward and reverse bias of a PN junction is, okay, in a PN junction diode, which is the dominant mechanism for the motion of charges? Drift, forward bias, diffusion, reverse bias. Come on, this is simple. Let's go back quickly. For forward bias, what was it? For forward bias, the diffusion is dominant. Do you see that? Diffusion. This N to P type diffusion conducts the electricity. Whereas in reverse bias, it's the minority which is the reverse bias. That means, it's the minority charge carriers. So there we go. That's a drift current. Diffusion is because of the majority. Drift is because of the minority in reverse bias. Okay, I just explained that to you. Next, the IV characteristics of a PN junction diode is shown below. The approximate dynamic resistance of the diode when forward bias of 2 volts is applied is how much? Let's try to figure this out. It's not that difficult. The current versus voltage characteristics are given. Okay. So the question is, what is the dynamic resistance? I just give you the formula for dynamic resistance. It is del V by del I. I think you can easily look at this over here and realize this value is del V. This value is del I. So how much is del V? It's obvious, 2.1 minus 2, which is 0.1. And del I, that's 800 minus 400, which is 400, but milli. So 10 to the power minus 3. I hope that makes sense. So basically, this will be nothing but 0.1 divided by 0.4. So that is 1 by 4, which is 0.25 ohms. Do I have it somewhere? Yes, I do have it. Perfect. That's the answer. So it's just the slope of voltage and current graph that gives you dynamic. If it was static, then it will be just voltage by current. Remember the difference, static and dynamic. Okay, let's see if we can solve this one. Of the diodes shown, which of them are in forward bias, which of them are in reverse bias? Come on, try to answer these questions. Some of them are in forward bias, some of them are in reverse bias. Which one are they? Okay, I think this should be easy one. You can pause the video also and have a look at it. Come on, think about it. I think it should be obvious from here that the option should be C. I'll tell you why. Look at this. In option C, ground means 0 volts. This is 5 volts. Reverse bias, right? This is P side, this is N side. N is at higher volt. P is at lower volt. Obviously, this is reverse. You look at anything else. Let's say, for example, here. This is P type, this is N type. P is at minus 5. N is at minus 12. Obviously, minus 5 is higher than minus 12, negative number. So P is at higher voltage, so forward bias. Here also, this is 0 volt. This is connected to minus 10. This is P side and this is N side. Obviously, 0 is more than minus 10. Obviously, forward bias. And the same thing you can say over here. This is P side and this is N side. P's voltage is more than N. So this is also forward bias. Hence, the only diagram which is in the reverse bias is option C. Correct? Let's move to the next one. The diode used in the circuit shown in the figure has a constant voltage of 0.5 volts at all currents and a maximum power rating of 100 milliwatts. What should be the value of the resistor R connected in series with the diode for obtaining maximum current? Let's try this out. It's not that difficult. The question is, what should be the resistance so that the maximum current is obtained over here? Okay, let's try to do this. Let's say the current over here is I. 0.5 volts is dropped here. So if 0.5 volts is dropped here, and I know totally across this 1.5 volts is dropped, then obviously across the resistance 1.5 minus 0.5, which is 1 volt, is dropped. Make sense? 1 volt is dropped. Fair enough. Now, once you get this, let's try to see, do I know certain values? The power is given. I don't know the current in order to find the resistance. So I can find the resistance by finding the current. But to find the current, I think I need to make use of the information given for the diode. For the diode, the power of the diode will be voltage into current. So think about it. Power is given to be 100 milliwatts. So 100 milliwatts. This will be voltage. Voltage is 0.5 volts into the current, which I do not know. So the current will be 100 milli, means 100 into 10 to the power minus 3, 0.5 volts. So 0.5 will come over here. So this will become 0.1 by 0.5, which is 1 by 5, is the current, amperes. Now think, if I know the current, can I find the resistance? Yes, V is IR. So voltage across the resistance is current into the resistance. So voltage is 1 volt, current is 1 by 5, and resistance I don't know. So R will be just 5 ohms. Simple circuits. That's all. So the answer should be 5 ohms. Got it? Very, very easy problem. Okay. Now we will talk about light emitting diodes, and we will talk about photodiodes and Zener diodes, etc., which is the next part of this chapter, in the next class. Okay, so I'm going to divide this chapter into 2 parts. The first part will just have semiconductors, PN junction, diodes and its characteristics. Now that you have a hang of it, in the next part we will start with LEDs, we'll start with also Zener diodes, transistors, and then logic gates. So if you have enjoyed this class today, do let me know in the comment section, and also do not forget to make sure that you check out the links which are there in the description box to enroll yourself in the crash courses which are available to you at very discounted prices. And JEE Mains is not far away. Crash course will be available to you at 8,000 bucks after you use my coupon code SHHPRO or SHHCC. You can see, in fact, there is an offer running right now where you get the crash course for 7,000 rupees, much lesser than the quoted price. So go ahead, check it out. You get all the test series and obviously the lectures and assignments in this crash course. So thank you very much for tuning in. I hope you had an interesting session. I know I had planned to complete till Zener diode, but I have just completed till the diodes part. The next part will be coming up very soon. Don't worry. Okay. So wait for lecture 2. Make sure you hit the like and the subscribe button. Have a great time. See you. Hasta la vista. This was Capto Shreyas.